watersheds around the world, major policy goals have been set to improve water quality. In many of these areas, net input of nitrogen to watersheds have decreased because of improved fertilizer management and decrease in atmospheric nitrogen deposition. In almost all these cases, insufficient improvements have been observed in the receiving water bodies. Chesapeake Bay, here in Figure 1, is a prime example of that. Since the 1980s, scientists and policymakers have spent millions trying to reduce nutrient loadings, but we're still seeing algae blooms in the bay to this day. Increased nutrients into the receiving water bodies can severely alter the ecosystem and can ultimately lead in decrease of ecosystem services. Shown in Figure 2 here, the Eastern U.S. has seen a significant yearly reduction in deposition of nitrogen. Although there is a decrease in nitrogen and fertilizer use efficiency has improved, we are not seeing proportionate decreases in stream nitrogen concentration, which leads us to believe that there is time lags within the system. So by time lags, I mean the time it takes for decreased nitrogen inputs to result in a decrease in stream nitrogen concentrations. The primary research question that we want to answer in this project, some of which will be discussed today, is what is the magnitude of the time lag in the Eastern U.S. and what are the dominant controls within the water basins. As shown in the figure up top here, all of the net nitrogen inputs are taken with respect to the watershed boundaries. As for the stream nitrogen concentrations, riverine concentrations are used to find the amount of nitrogen exiting the system. Cross-correlation analysis was used to quantify the time lags between the peak of nitrogen inputs and the peak of stream concentration. So starting off with the Grand River watershed, we can see in Figure 3A and 3B that although the inputs are similar, the response to the decreasing nitrogen inputs after the 1980s are significantly different. In Figure 3B, there is an estimated time lag of 12 years. This shows that the nutrient dynamics of the subwatershed are less driven by nutrient legacies. Alternatively, there's 3A, and even though the nitrogen inputs begin to decrease after the 1980s, the stream nitrogen concentrations are not decreasing as quickly. The time lag within the subwatershed is estimated to be 26 years. This means that there's nitrogen legacy within the watershed. So as we can see in Figure 4, the time lags vary throughout the watershed. It was found that there's longer time lags, and they were focused around the forested areas with lower nitrogen inputs. The shorter time lags were found in areas with larger populations, so more wastewater treatment plants, and more tile-drained agricultural land. So now moving on to the Susquehanna watershed. The Susquehanna watershed is found in northeastern U.S. Based on preliminary analysis, we found that there was no significant time lags within this watershed. However, this result is deceiving. In the 1980s, wastewater treatment plants began to be upgraded. So the decrease that we see in stream concentrations after the 1980s is likely being driven from these point source controls. After 2000s, the input decreased, but concentrations remain nearly the same. This leads us to believe that there is legacy within the watershed, but further data processing is required to tease out those results. Understanding the dynamics of such a system is critical for policymakers and engineers to maintain dedication to this time and cost-extensive management practices. It may take decades for nutrient loadings to decrease and receiving water body to improve.